All right, any problems on that 27 through 33 odd, or 39 through 42, or 45, 46? 46 for sure. Okay, we can talk about that one. 45. 45. Okay. So none of them really on the sigma converting.
Well, how did they get like? Sometimes they gave you the exact same one, and then they got a different answer when you put that variance.
On that first section.
Yeah.
With the shift, was it with the shift kind of thing? So which one specifically? So that, I mean, that's good. We should talk about it. So like number.
Like 27 and 28, they did like instead of just leaving the inside x, they do 4 plus x.
Right, that's exactly what's going on there. So on 27, 28, and you, if you look at those, I think maybe I said the odd ones there, but I mean this is really good to look at. If you look at 27 and 28, they're the exact same sigma, right? And so what it says there was, what did it start I at? 0 or what? Or was it K? Or it's K, but doesn't matter, whatever. So it's 1 to n. Okay. So we got 1 to n. Okay. 1 to n, and then it's got 4 plus I over n, or k over n, right? Cubed. And then what was it here? 1 over n. Where was the 1 over n? Was that on the other side of the segment? It was on the other side, which is fine. It was here, and then there was this limit as n goes to infinity. Now, do we care about that limit part? I mean, what's that doing there? It just means there's an infinite number of rectangles, right? So that means it's going to actually be the exact area, right? It's not going to be an approximation. It's not going to be 10 rectangles or 20 rectangles. It's going to be an infinite number of rectangles, all that means. And then this is the width. This is the dx. So when we go to this, one way of doing it, like they did in 27, is the way we kind of preferred to do it, is we said, okay, this is the dx. This is the messy stuff that becomes the x. So over here, we're going to have just x cubed. And then what is our starting point? And so like Jamie was saying yesterday, if they're right rectangles, we can just plug in a 0 here, right? And you get 4 plus 0, which is 4. And then plug in n as your last one. Two ways to do this. You can plug n as your last one. You get 4 plus n over n. 4 plus 1 is 5. Or you could say the width is 1 over n, and you have how many rectangles? N. So the total width has to be 1. So if you start at 4, you end at 5. So that was what they had for number 27. And that's how we kind of talked about doing it. Now, the other way you could do it, if you don't think about Jamie's method, where you put a 0 in here, since they're right rectangles, you're going to start one width over. So you put a 0, that'd be your actual left edge. You could just put a 1 in, and it's 4 plus 1 over n. Well, 1 over n is your width. So if you're 4 plus 1 over n, that means you're one width over from 4. So 4 had to be your starting point. So that's a way to think it through. Now, the other option is kind of the thing with the shift. Some people look at a problem like this and say, well, here's the messy stuff, the stuff that's changing, you know, the 1 over n, 2 over n, 3 over n. Let's let that be our x, right, instead of the whole, including the 4. So then what they're doing is they're saying, okay, so then the function is, this is where the x is. The x is the variable, right? X is the changing thing. And so the 1 over n, 2 over n, 3 over n, that could be where the x is. And so this function could be 4 plus x cubed. And the 1 over n, of course, is still the dx. Well, the difference there is, then where is your x starting? Well, if we're only looking at the green part right now as our x, then I wouldn't say 4 plus 1 over n, 4 plus 2 over n. I would just be thinking to myself, 1 over n, 2 over n, 3 over n. Well, if 1 over n, what came right before 1 over n? 0. Or do Jamie's method, plug a 0 in for I. You're only looking at the green part because that's what you're calling the x. So you put a 0 in, you get 0 over n, which is just 0. So your starting point in that case must have been 0. And since there's a total width of 1, right? But all this is a shift. This is just the cube that goes from 4 to 5. shifted left 4. So if you shift these two numbers to the left 4, that's what you get, right? So that's why they did that. So those are both okay answers. So 27, 28. I don't care. So tomorrow, what will it look like? I'll give you this and say write the integral. Either one of these would be okay. Either one is fine. Okay? My guess is most of you would do that. Right? Now, while we're discussing that, it might make sense actually to go here to sample your sample 1 packet. Why don't you go ahead and turn to that, because that kind of comes up here. Your sample 1 packet number 28. So this is like the one we did yesterday in the sample 2 packet. Okay? Now they didn't write it as a sigma, it's all written out. Now you could write it as a sigma if you want. Matter of fact, that might not be a bad idea. Be good practice anyway. Okay, it'd be a decent practice for this anyway, so let's just do it. So let's do our sigma. There'd be a 1 over n, which we can pull out in front here for this part, and there'd be this limit, as n goes to infinity, whatever. That would all be there. And then look at each one of those terms, and let's look at the pattern. So what's it look like? It looks like it's 1 over 1 plus what? I over n. And then the I is going from 1 to n, because that last one is an n. So we got a 1, then a 2, then a 3, then a 4, then it ends at n. So 1 to n. So these look like they're rights. Now, the one yesterday in sample 2 actually went from 0 to n minus 1. So they were more lefts. But it was a little confusing because they left out the 0. And so it didn't look like it would be a left. But that's what you get. Okay, so now if you're going to write this as an integral, okay, this 1 over n, of course, is the dx part. And so the question is, what's your function? Now, you could get a little thrown off by your choices over here. So to be honest, I would right now, let's don't pay attention to those choices over there. So if this is one you had, if this is one I gave you tomorrow in the quiz, what are you going to look at for where the x is? I would say the way I first taught you to do it is to look at that and call that your x. I would say the messy stuff there, the stuff that's changing is that. 1 plus 1 over n, 1 plus 2 over n, 1 plus 3 over n. So I would say one way of doing this would be to think of that as your x, so there's your function. Now where does that start? At 1, right? We've talked about how when you have a 1 plus in the messy stuff, like the last one had 4 plus stuff, the 4 is a starting point. So I would agree, 1 is a starting point. Because what do you got? You got 1 plus 1 over n, 1 plus 2 over n, 1 plus 3 over n. So 1 must have been your starting point. And then where's the ending point? 2. Again, because the width is 1 over n, and you have n rectangles, so that's a total width of 1. So it's got to go from 1 to 2. Or plug an n in. 1 plus n over n, 1 plus 1 is 2. So I would say that's how you would do it tomorrow. Now, tomorrow's not going to be multiple choice. However, you come over here and look, is that one of the options? It is?
Yeah.
Oh, good. Oh. I didn't think it was going to be. Okay? I didn't think it was going to be. I thought they were going to do this to you. Let me do it in black. So the other option would have been to call this the x, right? This is the part that's changing, really. 1 over n, 2 over n, 3 over n. So I could have written this one as 1 over 1 plus x dx, but then it would have started where? At 0 and went to 1. I actually thought that was going to be one of the choices here, but it's not. But I could have seen them doing that, right? That's the deal with a multiple choice. Maybe down here, maybe they didn't include this choice, but they did include that one. So you'd have to know the difference, right? Or that they're the same. This is just a shift to the left 1 of the 1 over x function. It's x plus 1, which is a shift to the left of 1. So these two are the same. So again, tomorrow on the quiz, if we have that situation, that either one of those would be acceptable. Okay? All right. So, good, that's that. So let's look at 45. So 45 gave you that table, I believe, right? So 45, okay. And I said you didn't have to do parts A and C, just part B. So estimate the total distance traveled using 6 trapezoids. Okay, so now first of all, the only time we really have to worry when we have a table is if they're equal widths. Because if they're not equal widths, then we gotta worry about it a little bit. We'll look at one here in a minute. Okay, but if they are equal widths, then we don't need to. We can just start writing this down. What do they call that function? They don't really call it anything, right? I'll just call it f. So how would a trapezoid look? Where would I start? Now it goes from 0 to 60, right? And we're going to divide that into 6 subintervals. So 10 wide, right? So this would be 1/2.
We're going by miles per hour, so going by hours would be 1/60.
Okay, good. I was just going to wait to see when somebody caught that. The units don't match here, do they? Right? Our x units are minutes, and our y's is miles per hour. So you got a couple of choices. You could go ahead and do it with the tens, and you can adjust it at the end. You didn't catch that? Yeah. So you do have to. So let's say we didn't catch that, and we could adjust that at the end, right? By just dividing by 60, right? Just dividing by 60 because there's 60 minutes in an hour. So let's say we didn't catch it. So we go in here and we go, okay, they're 10 wide. So what would my first trapezoid look like? It'd be f of 0 plus f of 10, right? I mean, that's how trapezoids always look. They start at the left edge and then go to the next width. If the width is 10, you'd have that. And then times a width of 10, but let's say we didn't notice that, right? So we're going to go 10. Okay, plus 1/2 f of 10 plus f of 20. Now tomorrow, and then that's times 10. Remember, I said if it's single digit number of subdivisions, I want you to write it all out. You're going to have to do that tomorrow. That's one of the things we'll review here in a minute, but this is good review right now. If, one of the first things we did in section 6, I had you draw 6 left rectangles or 6 trapezoids. I might have you draw this one, right? I might have you draw this one. Or if I give you an equation, we'll get to use calculators tomorrow. So if I give you an equation, you might want to graph it on your calculator and then sketch it and then draw in the thing. So I didn't have you draw it here, but you're going to have to be able to draw some left rectangles or some right rectangles or some trapezoids or some midpoint rectangles. Probably not all those, but you will do at least one drawing of those things tomorrow. But you do have to write this out, okay? So let's go ahead and keep doing it. So that'd be f of 20 plus f of 30 times 10 plus 1/2 f of 30 plus f of 40 times 10 plus 1/2 f. And what I want to talk about here, whoops, f of 40 plus f of 50 times 10, and then I think I should have one more, 1/2 f of 50 plus f of 60 times 10. So there's my 6 trapezoids, and now I just plug the numbers in, right? And so I can just write those up above in red. So we have 42, and we have 38, 36, 57, 0, 5. Okay, and so now you guys on your calculator, you would add those all up, multiply as it needed to be. Of course, the 1/2 times the 10 make 5 on every one of those, so you can simplify that a little bit on each one of those. But final answer was what? 2,000. Okay, is that the right answer? No. Here's where you should catch it. If you didn't catch it at the beginning, like Jamie asked about, you would say, okay, we're going about 50 mile an hour, 40 to 50 mile an hour for an hour. Is it plausible that we just traveled 2,300 miles? No. Right? Probably not. So you should catch that at that point, right? And so what you can do then is divide by 60 and then that would give you the right answer, okay? Or the other thing we could have done is at the beginning, notice, okay, that's miles per hour, so let's turn those minutes into hours. So 1/6, 2/6, 3/6, 4/6, 5/6, and 1, or 6/6, right? And then we'd have had 1/6 here as our, instead of 10. We'd had 1/6 in all those spots. And then it would have come out right. But I would be okay if you did this and then adjusted it. Okay, so that's a good one just from the standpoint of making sure our units match up. Okay, and knowing that we got to write those out. Now, again, let's look at one that would be a good one. Let me see, I can't remember if this is back in that sample packet. Yeah, here's an example. Now this is on your calculator. Just go to number 32 here on sample 2. Go to number 32. Or sample 1. This is still sample 1. I'm sorry, same packet we just done. Okay, so it says some values of a continuous function are given in the table above. The trapezoidal rule approximation for 0 to 10 is. Now, what do you notice in that problem? They call it the trapezoidal rule, but as you go to calculate that, what do you notice is missing? They want you to do a trapezoid rule on the integral 0 to 10. They didn't say how many. They didn't say how many. So what would you assume? 10 of them, one line. I think that's what you would typically do. You would assume you're going to use all of that, right? So, now, this might be a good time. We're going to talk about it later in chapter 6, but what the heck, we might as well talk about it now. If you were looking for kind of a shortcut for all of this that I just did right here, what do you notice it just repeats over and over again? The 1/2. The 10, can you pull those out and just do those at the end? And if you did pull out the 1/2 and the 10, what are you left to add up? That y value, 2 of the f of 10s, 2 of the f of 20s, right? Because the right edge of this trapezoid is the left edge of the next trapezoid, right? What are the only ones that go just twice? The left edge and the right edge. You use those once, and you use the other ones twice. This is actually often written out in that way. Often the trapezoid rule is written this way. It's written as 1/2 times the width. Those just pulled out in front, right? Because the 1/2 of the width is going to stay the same. And then in here, f of x sub 0 plus 2 f of x1. We're going to write it this way later in chapter 6. 2 of all of them until you only get 1 of the last one, like that. So by the time we get to the AP test and stuff like that, wouldn't that make this one a lot easier? Because you'd have 1/2, what's your width? 1. And then so now you can just grab your calculator, and all you have to do is add up these y values, except you're doing 2 of all the ones except for the ones on the end. So you would just have this plus 2 of those, plus 2 of those, plus 2 of those, plus 2 of those, plus 1 of those. You see what I mean? And you can just sit there and add those up, and then times by 1/2 at the end, and you'd have it, right? Instead of writing it all out and thinking about it, right? So if you had a trapezoid one like that tomorrow, with a table or something like that, I'd be okay with you doing it. You think of it. Or if you're more comfortable, just, it is a quiz, and so you do, it's kind of like my Algebra 1B kids. I was always looking for shortcuts. They get kind of lazy. We all do sometimes. But they were looking for, we were doing some factoring and things like that, solving. And we're doing problems like this. We're solving, we're doing factoring, you guys know what I'm talking about. And they're doing that. Now, when I taught them to do this, I had them write out both of these equations and solve them. Well, some of them said, oh, can't you just look at that and tell it's going to be -1 and 3? Yes, you can. Good job. However, can you do it accurately and correctly? And then what happens when you get this one. Can you do that one in your head? Yes. Can you do that one in your head?
Yes.
I think you guys can. I hope. But some of them do not. And I said, you know, if it was me and it was a quiz and that really mattered, I might take a few extra seconds to write that out and solve it. But whatever, it's up to you. Okay? Well, that's kind of what I'm telling you guys here. Right? If you're more comfortable, you know, writing out your 6 trapezoids to make sure you got them there, whatever, and you know, get the right answer, then I would encourage you to do that. Okay? Before we go on to that next one, let's look at that other packet I had you take out, the 2015 one, and let's go to problem number 3. Let's take a look at problem number 3. So this is Johanna, I don't know. Johanna, is it Swedish? Maybe that's a Swedish spelling, I don't know. Yeah, I don't know. So anyway, so this is from last year's, these are the 3 response questions from last year's AP, okay, last May. So she jogs along a straight path from 0 to 40. Her velocity is given by this differentiable function v, so this is meters per minute. Notice that the units match, not like the last problem we did. Selected values are given. And so let's go to, well, we don't really need this for tomorrow, but what the heck's a good one to review. How would you estimate v prime of 16? V prime means derivative, right? How would you find the derivative of 16? Pick these 2 points and do a slope. So 240 minus 200 over 20 minus 12. 16's right in between there. 40 over 8, which is 5. It didn't say anything about units. It just said the value. But if it were me, I think I would put units just for the heck of it. Now, I think in the grading of this, on the AP test, they are pretty picky or pretty careful with how they word their questions. Notice in B, it says, using correct units, okay? So they're pretty, if they want you to have the units, if that's going to be a big deal, they're going to get points for it. A lot of times it says it. Now, I'm not always that careful on the wording of my question. I would put units if I thought it might be an issue. So what would they be here? Meters per minute squared, right? Meters per minute per minute. Because V, the units on the top are meters per minute, and we're dividing by minutes. So it'd be acceleration, right? Acceleration. All right, but that's not the one I really want to do. I want to do part B. Using correct units, explain the meaning of this definite integral in the context of the problem. The integral from 0 to 40 of the absolute value of velocity. We've talked about it within the last month, I know. What is it when you do the absolute value of velocity? Speed. It makes all of those velocities positive. And what is it when you do the integral of that? No, it's distance. But what distance? There's 2 different distances. There's net distance traveled and there's total distance traveled. You have 50-50 shot. Think about which one would not include a negative. Total distance traveled, right? Because if I go here and walk this way, which is a positive velocity, and then I walk back this way, which is negative velocity, and right here, my net distance traveled is 0. So if I include the negative part, those areas, think of it, those areas would cancel each other out, wouldn't they? And that would be net. So if you think about a regular velocity graph, it could go up above the x-axis, and it could go below, and these areas here would cancel each other out. That's net distance traveled. But if you take all the negatives and put them up positive, now you're just all positive areas, so now you're total distance traveled. So this, what they would want you to say is this, a good answer for part B would be to write out the total distance Johanna jogs from what? 0, using correct units, 0 minutes to 40 minutes, or during this 40-minute interval from 0 to 40, and I should put in what are the units on her distance. What would be the units on her distance? Meters. So this integral would be the total distance in meters that Joanna traveled during these 40 minutes. That's the answer they're looking for in part B. Okay? Then it says approximate this value using a Wright-Riemann sum with the 4 subintervals indicated in the table. Okay? So a Wright-Riemann sum, now you don't want to use F here because they've named the function V. So the Riemann sum would be V of, that's a right, they said. So V, not F, V of 12, the first one to the right. We don't use 0 if it's right. So V of 12 times, what's the width of the first subinterval? 12 plus V of 20 times 8 plus V of 24 times 4 plus V of 40 times 16. Now I hope this is a calculator one. Is it? Oh, yay. All right. Now remember, this is absolute value. So when we get to V of 24, we're actually going to use the positive value. I probably should have bars around all of these. I'm not sure they necessarily awarded any points for writing it out. I would anyway, so I don't think you would lose points if you wrote it out and didn't have bars. But they're going to look for that answer. So it's going to be 200 times 12, which would be 2,400, plus 240 times 8. Jeepers. $19.20 plus 220 times 4, what's that, 880, plus 150 times, what was it, 16, $2,400. Did I do that right? That's right. That's right. The 3's. Wait. Yeah, no, that's right. That's right. Okay, so that's 4,800, 5,680 plus 1920. So what is that? 7,600. 7,600, and that would be meters, right? And we said that was total distance travel. Total distance travel. Now that kind of makes sense, because if you do kind of an average, it looks like it was about 200. It looks like it was about 200 meters per minute for about 40 minutes. 200 times 40 would be about 8,000, right? So about 8,000 meters. So that seems reasonable. Okay. So again, Wright-Riemann sum, but it's different widths, right? So we would have to treat it that way, but they wanted a Wright sum. Okay? All right, just some different looks at those kind of things. All right, now let's go on to 46 and look at that. Now, 46, we didn't know what the functions were, which is fine. We didn't have equations, didn't have graphs, didn't have tables. We just had names for them. And that's okay. Whoops. And so it was E. One of the functions was E. What were the units on E? Kilowatts, that was it. And what was C? Dollars, that was it. Cost per, it was dollars per kilowatt hour, which means kilowatt times hours. That's what kilowatt hour is. Okay? And then, are you sure on E? It was just kilowatts. Okay. All right. So they want us to write, and let's do the sigma first. Actually, the integral would be easier to write first, okay? But it doesn't really matter. I mean, let's do it with the sigma first. T is from 0 to 24. The power company's rate. Okay, assume set up an n-term left sum that approximates the cost of the electricity consumed over a 24-hour period. So what I would do in this situation is I would say, okay, we're going from 0 to 24, right? We got a 24-hour period. That's our T, like our x-axis. Okay, and we're going to do how many terms? No. How many terms does it say? N. We're going to do n terms, right? We're going to do n terms. Okay? They use the uppercase n, but I'm going to use lowercase n. And so what is our width? Not 1 over n. 24 over n, right? What's our total width is 24. We're going to divide that up into n subintervals. 24 minus 0 divided by n, which is 24 over n. So our width is going to be 24 over n. So this first one here would be 24 over n. And the next one would be 48 over n. The next one would be 72 over n. And so forth and so on. And this last one would be 24n over n, right? Like that. Set up the same way we always have, right? Now, then we go in here and we say, okay, and I'll use f. I know I've got these two different functions here, so we're going to get to this in a minute. And what I want to do is add up that cost, but then the question is going to be, how do we get that cost? Which that's the new part to this. That's the story part of this. But let's forget that for a minute, and let's just say our function's f that we're adding up. So I'm going to do a sigma, and I is going to go from what to what? Now, are these left, rights, or what? They're, what's it say? Left. Okay. So this is going to go from 0 to, no, not 23. N minus 1, right? Remember, the sigma is how many subdivisions you have, not the 0 to 24. That's going to be in the integral. The integral is going to go from 0 to 24, right? This tells us how many subdivisions we have. We have n subdivisions. But since it's a left, it's going to be 0 to n minus 1. If it's a right, it'd be 1 to n. Now, we can set it up like it was a right. That's fine, remember? Because rights and lefts are the same. It's just that lefts have this on them, the 0 to n minus 1. Okay? So we can still look at it as just, with our eyes, just setting up this. So let's just pretend the function is f. So f of what? Well, 24 over n, 48 over n, 72 over n. How do we generate that with i's? 24i over n. And then my width was 24 over n, right? So this would be a pretty good answer to part A, except we haven't used our functions that they wanted us to, the e and the c. So we got to figure out how we can use those, okay? But this would be it, okay? There'd be our width. There'd be because if we plug in a 0, we're going to get f of 0, which would be our left edge. And then when you put in a 1, we get 24 over n, 48 over n, and so forth. So we would get, okay? So there it is, just like we've been doing. But now this is supposed to represent what units? What is this integral supposed to represent? Unit-wise. The cost in dollars. So we want this to be dollars. So the question is, how can I use these? And that's, oh, what's 24 over n, by the way? What's the units in that? That's time, which is hours. So we actually want our f function here to be dollars per hour, right? It's like the last problem we just did. We were adding up those velocities, but then we times them by the width. So we had meters per minute times minutes, or is meters per hour. What was it in that problem? It was, in this problem we just did here, it was meters per minute and then minutes, right? So we were taking meters per minute height times minutes, right? So what we want this integral to be is dollars per hour times hours, right? And that'll give us dollars that we'll be adding up. So how could we get a function that would be dollars per hour out of these two here? How can we get dollars per hour out of these two right here? Can we just multiply? Kilowatts would cancel. So what I'm going to do then for my answer is I'm just going to replace. Now this is not going to be, I would not worry about this too much for the quiz, really. I mean, this could be a little piece of one problem, maybe with some units, but not really a major thing. But the idea is that we just want these units to give us what we're trying to add up. We want to get dollars. And so we're going to have dollars per hour times hours. I mean, think about what we're doing here. Like we just said, we wanted to do the integral of miles per hour that would give us miles, right? That's what this sigma is like an integral. So if we want dollars, we should have dollars per hour in here. So all I got to do is multiply those. So it's going to be E of, gosh, why do we keep doing that? So many sigmas. Right, E. Okay, so it's going to be E of 24I over N times C of 24I over N. And then times the width, 24 over N. Okay, so that's something we're going to be doing a lot more of later, where we want to set up these sigmas, or mostly we're just going to set up integrals, not sigmas so much. Where we set up these integrals that will give us the units we want, right? So if we know what functions we're given, just put them together as units. Really pretty easy. We just had to multiply them to get the kilowatts to cancel. Okay, so there's the answer to part A. Okay, I'm mostly interested for the quiz that you recognize this stuff that we did, where we got the width, 24 over N, we could show our x-axis, and we could think about writing the sigma. Now, what's the integral going to be? The integral should be easy then. That's just what we were doing today. These two are going to actually, this messy stuff's going to get replaced with what? In this problem, not x, so t. So this is just going to be E of t times C of t. Remember, sigma, messy, integral. The other class came up with, or did you guys come up with tidy? I think the other class, we were talking about what's the opposite of messy. Somebody said tidy. I said, oh, tidy. Okay, that's it. But sigma, messy, integral, not messy, right? Neat, clean, tidy, whatever. This part is what?
dx.
dt in this one, okay, dt, and then the integral goes from 0 to 24, right? 0 to 24. So that would be part B.
So there would be one like this one.
No, well, as far as being able to take that sigma and write it as an integral, absolutely. Being able to subdivide and that kind of thing. The story problem type with the units, probably not. I mean, I wouldn't worry too much about that. Okay? All right. So, let me give you one last problem, then we'll talk about just go over some general things about the quiz, and then I've got a few review problems in the book you can work on here. Okay? So let's take this one, because that whole thing about the n, that sounded like you were a little uncomfortable with that a little bit. So let's do this. We've done some R10s and R50s and stuff like that. We haven't done as many of this. So let me give you just maybe a little simpler version of the one we just did. So let's say we had the integral of x, what do I got here? X squared. Let's just say it's x squared dx. And I want you to write an R sub n approximation. I want you to write a sigma for n right rectangles. Okay? Give that a try and see what you come up with. Write the sigma that would represent n right rectangles. And you can help each other out and talk about it. Just going in. So then you would take this sigma, that'd be what, 9i squared times 3, that'd be 27 n or I squared over, and then this would be n squared times n, that'd be n cubed. Well, the 27 over n cubed could just come out here, and then in here we'd have sigma I squared, right? Everybody see what he's doing? Okay? And then you would use those formulas. Now, what I might do, what I probably will do, because we'll talk about it in a second, but yeah, using those formulas is something you're going to have to be able to do, but probably I'll just give it to you as a sigma problem. You know what I mean? Here's the problem with doing all of this in one problem, is if you screw up the sigma, then you can't get the last part of it right either, right? So what I'd rather do is give you a problem where you have to write the sigma, give you a separate problem where I give you a sigma and say, now use your formulas to find the sum. See what I mean? But this is what this would look like. So let's say I just gave you this sigma and said, hey, find the sum using the formula. So it'd look like this. You'd multiply that out, you do that, you'd pull out the constant, which is this part. What was sigma I squared? That was n times n plus 1 times 2n plus 1, right, over 6, I think. And then we would have that times 27 over n cubed. So that would, now you'd have to, what would I have added? If I was doing n of these, what would I have added to this?
What, n equals?
No. Well, I could have done an R10, right? So if this was an R10, then these would all be 10s down here, right? The n would be 10, and this would be 10, and that'd be a 10 in there, right? And I would have a number to actually plug in, and you calculate it. But if I was using n, what would I usually do from here? What did we do at this point? If we're doing n rectangles. We did this, right? When we did n rectangles, that's typically when we tacked on, hey, and then let's look at as n goes to infinity, which means an infinite number of rectangles. And so then you could take this and you could say, okay, now what as n goes to infinity? Well, you'd have 27. The top high power would be 2n cubed, and then the bottom is 6n cubed. And so that would be 54 over 6, which the n's cubes cancel, right? And 54 divided by 6 is what, 9? So the answer would be 9 if you had the limit here, if you had the limit as n goes to infinity, right? And if this was R10, then you'd have 10s all in here, and then you'd have actual numbers to plug in for the n. So it could be that way too, okay? And then, of course, the cool thing about that is if we go back and we check this, if we check this with fundamental theorem part 2, right? What's the antiderivative of x cubed, or x squared?
X cubed.
1/3 x cubed, from 0 to 3. Plug in a 3. 3 times 3 cubed is 27, times a third is 9. Put in a 0, right? We know this actual area is 9, and what we just showed, this is like that one we went through that one day. And if you add up an infinite number of rectangles, you also get 9.
So
Nine
can we
gives-
just do that?
Okay, what's that?
Can we just do that antiderivative then?
But it just depends on what's being asked, right? It just depends on what's being asked. Yeah, this quiz is not, that was what the gateway was about. So I don't think there's going to be any problems on here where I have you do that, unless it's part of a problem where I say, hey, do 10 right rectangles, and then compare that answer to the exact area that you get using the fundamental theorem of calculus, right? So then I would want you to do the fundamental theorem of calculus, get the exact answer, compare. So I might ask you that. As a matter of fact, let's talk about that. Let's just talk about what the quiz is. Okay? Yeah, you should absolutely be able to do that, but you're not going to have choices. You're not going to have to sit there and think, God, should I do the exact area? Should I do this? It's going to say, right? The director will say what I'm asking you to do. Okay, so for the quiz, 5.6. First thing we did was be able to draw left, right, midpoint, and trapezoid. So some sort of a picture. I give you a graph, or maybe I give you an equation. You're going to get to use calculators here, so if that helps you draw the graph, okay? So I'm going to give you, you're going to draw some rectangles, right? So if I give you some function here, integral from 0 to 2 of x squared dx, whatever, and I want you to, so you're going to draw the x squared graph from 0 to 2, you're going to put in 4 left rectangles or whatever, shade them in, okay? And then I might ask you to calculate, right? So you're going to calculate those, right? Like 4 lefts or 6 trapezoids or whatever, okay? Be able to do that kind of thing. And you want to be able to do those with graphs, equations, I think I spelled that wrong, but whatever, and or tables. So we've done several here with tables as well. Okay, so you want to be able to calculate these sums, with tables, with trapezoids, with. Now I kind of skipped around that on 45. Everybody okay on 45? There were different parts to 45 actually worked. We just did one, right? You were supposed to do 6 trapezoids, but there was also some lefts and some right trapezoids. Okay. So we'll have some time here if you want to ask me about those. We can look at it. So you want to be able to do those. With any of those. So probably multiple questions. I don't know how many I'll make you draw, but calculate, probably going to have to do some calculating on a few of them, right? And have to work it out. Now, whatever I give you, I told you if it's single digits, but really don't worry about that. If I give you 10, there's 10 you have to add up, you have to add up 10. I mean, I told you I was going to give you a program, like if we want to do 50 or 100, that's more in chapter 6. We get in chapter 6, we'll be doing some, want to look at 100 midpoints or 500 midpoints. We'll have a program to do that on our calculator. For right now, whatever I give you on this quiz, that's how many you have to do, right? How many you have to add. It won't be more than 10. I think 10 would be. So that'll be a big part of the quiz. And that's pretty much what section 5.6 was about. Okay? Then 5.7 is when we got, and 5.7 then is when we got into writing the sigmas. Okay? Taking an integral and converting it into a sigma. Right? Using the summation formulas like we just did. Right? And those will be given to you. Right? That we're talking about sigma I, sigma of a constant, sigma I squared, you know, those will be given to you on the paper, so you'll be able to use them like we just did on that last one. And then, of course, the last thing, what we were doing today is you start with the sigma and you convert that into an integral. Right? So we've done a little bit of both of those today. You know, we just did the one, we started with an integral, wrote the sigma. And then today's homework was starting with the sigma, right? That's about it, right? Then, of course, I mean, we did, in the midst of all that, we came up with the definition, the actual definition of the definite integral, right? That was the one that was the thing that said that, you know, in the definition of Riemann sum is rectangularities, right? Riemann sum is rectangularities. And the definition of the integral is that the definite integral, the exact area, is adding up an infinite number of left rectangles, or any rectangle, adding up an infinite number of rectangles. So that was, just right now, it's already in your notes, but we had the definition of a definite integral was this right here. Limit, right, n goes to infinity, sigma I equals 1 to n, f of c sub I, some sampling point times some width. So it's just rectangle heights. Rectangle height times rectangle area gives you, rectangle height times rectangle width gives you rectangle area. You add up all those rectangle areas, or n of them, and then let n go to infinity. That's an infinite number of rectangle areas. That's the definition of the definite integral. Okay? So, I mean, that's it. I mean, that's about all there was to it. So, for homework, I guess I've tried to pull, there is kind of a review page in this section, so I tried to pull some problems together here that would be maybe something that would be good review. The best review is just go back over those other, the homework problems we've already done, but here's a few I pulled out that these kind of focus mostly on the sigma and integral kind of stuff, I think. So that's like 6 problems. That's not very much, but there's not anything in there about the drawing aspect of it. So you want to go back to those problems we did with the graph paper, you know, and look at those again. Look back at those where you had to draw left rectangles, draw midpoint rectangles, that kind of thing. I don't think that was too difficult, but make sure you look that over. Okay, so that's all I got. The rest of the time you can work on those. Ask me questions on other stuff if you need.